Okay, if we look at the pattern on page 22, we have some patio tiles that are being used to make the patio larger. If we look at what's happening, there's kind of a change here in the middle because they have that same entrance and exit. So if we look at that rectangle here, it's a 1 by 3 across. Now we have 2 by 4, 3 by 5. So you can see that the height is getting larger by 1. So this design would be 4 high. And then for the length, we're going 3, then we have 4, then we have 5, then we would have 6, and then we'll have those 2 tiles for the entrance and exit. So 4 times 6 would be 24, plus the 2 entrance and exit would be 26 tiles. We can use the number of tiles to help us figure out what kind of a pattern it is. So if we count, we have 5 tiles here, 10, 17, and we just said design 4 has 26. So one thing that you can do is you can find the common difference, which is the difference between two values using addition or subtraction. So if we go with the difference between 5 and 10, that's a difference of 5. We have a difference of 7 here, and we have a difference of 9. If the numbers are fractions or it's hard to see the difference, you can always take one of the values and subtract the one that came before to find that common difference. So if we took 17, we'd subtract 10 because that's the one that came before, and that's 7. Well, they don't have a common difference. If they did, it'd be a linear pattern. So we're going to check and see if the differences have a common difference. So the difference between 5 and 7 is 2, and the difference between 7 and 9 is also 2. Again, I could have subtracted to find those differences. So it looks like they do have a common second difference. So what that tells us is that this is a quadratic pattern. So a quadratic, again, will have a common second difference. If we wanted to write an equation for this now, we can look at that change here happening in the middle, and it looks like this rectangle is getting larger and larger. So we'll always have these entrance and exit, which would be 2 tiles, plus in this case we have a 1 by 3 rectangle. If I do that for design 2, I have those 2 tiles plus a 2 high and 4 wide, so 2 by 4 rectangle. If I do that the same here, we have those 2 entrance and exit. We have 3 by 5. And we'll do it one more. We have 2 plus a 4 by 6. So for our equation, usually we'll use n or x. So I'm going to use n for the design number. And if we look in each of our expressions, we'll always have those 2 entrance and exit. So my equation is going to have 2 for those tiles. Plus, if we look, we had a 1 for design 1, a 2 for design 2, a 3 for design 3, and so on. So that's the design number high for the rectangle in the middle. And then for the length of that rectangle, we had design 1 gave us 3 across, design 2 gave us 4, and I'm starting to notice a pattern that 3 became 5, that is 2 more than the design number. So here's our entrance and exit tiles, because there'll always be 2, it's a number. We have that big rectangle in the middle, which is this part of our so there's our rectangle in the middle, And again, it's n high for the height being the same as the design number. And then the width is always n plus 2 because it was 2 more than that design number. Another way we can look at this pattern is to say that we kind of have 2 rectangles and then you have a square in the middle. Again, I have 2 rectangles and then you have that square in the middle, and the square keeps getting bigger and bigger, but you always have those 2 rectangles at the ends. So in this case, our 2 rectangles, we have 2 of them that are 2 high by 1 wide, plus we have, it's a 1 by 1 square in the middle. For design 2, we have 2 rectangles. They're each 3 high and 1 wide. Plus this time now in the middle, our square is 2 by 2. 2 high and 2 wide. And if we did the same with our third design, we have 2 rectangles, 1, 2, 3, 4 high, still 1 wide, plus our 3 by 3 square in the middle. So if we look at that, we're always going to have 2 rectangles. That's not changing any of the pictures. This height, we had in the first one 2 high when it was design 1, and the second one we had 3 high when it was design 2, and then we had 4 high when it was design 3. So I'm noticing that that height is 1 more than the design number, so I'm going to put n plus 1. Now I did say times 1 on each of these, but we don't need that in the expression unless we really want to put times 1, because we know that multiplying by 1 doesn't change anything. So I'm going to close those parentheses. And then for our squares, for design 1, it was a 1 by 1 square. Design 2 had a 2 by 2. Design 3 had 3 by 3. So I'm noticing that that is the design number times itself. So now if we compare the 2 expressions that we wrote, this purple one up here is the first one that we wrote, and this green one is the second one. We've also been talking about equivalency. So if I take that first expression that we wrote, those entrance and exit 2 tiles, and the rectangle in the middle that was n by n plus 2, if I use our algebra properties and I distribute, we can say that n times n is n to the second power, and n times 2 would be 2n. And if we write it in descending order, I'm going to put the n squared first, followed by 2n plus 2. If I take our green expression here and do the same thing, I can use the distributive property to multiply 2 times n, and then 2 times 1, and I can say that n times n is n squared. And if we write it from highest power down to lowest, we also have n squared plus 2n plus 2. So we have shown that those 2 expressions are equivalent. It just depends on how you want to look at it. If you look in the book, there's also Maureen's on the next page that you can take a look at. Maureen took it as a big square, and then she removed with subtraction these 2 rectangles. And then you have Matthew's, which also matches this n squared plus 2n plus 2.